So, welcome to class. So today is about modulus inequality, like I said yesterday. As the name implies, you'll be dealing with less than, greater than or equal to, less than or equal to stuff, okay? But involving the absolute value, okay? Now, just like yesterday's equation, let me show you. In yesterday's problem, we dealt with absolute value of ax plus b is equal to c as one case, right? And we dealt with absolute value of ax plus b is equal to absolute value of maybe cx plus d, right? In this case, all you have to do is apply the rule, which is that ax plus b is equal to what?
Plus minus c.
Plus or minus c. Good. And here there are two ways to go about it. You can say ax plus b is equal to
plus minus cx plus b.
Plus minus cx plus.
Good. Or you can square both sides.
Square both sides. Yeah.
And you have that. So these are the two ways we dealt with absolute value equation yesterday. So this is from yesterday. So for today, it's going to be absolute value inequality. Okay, we can write it short stuff. It's 5th of April.
The class has started.
Hi, Mr. Daniel.
Hi, Elson.
Sorry.
Welcome.
Get your iPad up to show your face.
Okay.
On the call to show your face.
Hey, just join the call.
Yeah, because you can't see your face.
It's okay, I think. I have to do my workings here.
Which satisfy a modulus inequality. Okay, so that's more like what we want to do. So again, there are two ways, there are two scenarios you can come across. You are going to come across the one with just the number, so just like yesterday. So you're going to be having these two cases, possible cases. So possible cases. The first one, you're going to be having ax plus b less than or equal to c. Of course, it could be greater than as well. And the second scenario, second one, you'll be having maybe ax plus b Rather than ax plus b, I should actually say f of x. F of x being a linear, because it could be rational as well. But it's okay. Ax plus b maybe less than or equal to cx plus d. Or it could be ax plus b greater than, or it could be equal to cx plus d. Okay. And it could have a rational function as well. So I write that as another scenario. So you could have ax plus b over cx plus d, the absolute value, less than or equal to maybe e. So it's the same, just like 1 and 2. So you could also have another rational. I will not expect you to be given two rationals. Something like this. Gx plus f, gx plus h, something like that. Of course, this could also be greater than or equal to. This could also be greater than or equal to. So these are possibilities, but the most common ones for you is this, and maybe this one. 4 is not common, but whatever you have in 4 and 3 are just like 1 and 2. The only difference is we have a rational function instead of just a linear function. Understand?
Yeah.
Yeah.
So the main clue here, or the main idea here, which this is something we have done in the past. Maybe I'll go to the next page for that. One sec. The main idea for how to solve for absolute value of ax plus b less than or equal to c. Now, listen. If the absolute value of a linear function is less than or equal to a number, it's either, if that number is positive, it means the entire function gives you the number. What I'm saying is this: absolute value of something is less than or equal to 5. It's either what you have in here is less than 5, less than or equal to the 5, or what you have in there is actually less than or equal to negative 5. Do you understand?
Yeah.
Mm-hmm.
Yes.
Let me put it this way. Or minus 5 is less than 8. I think that's what I should say for the other one. It's either it is less than 5 or it is greater than negative 5. Let's see, let me see what scenario I can give you. In this bracket, we have negative 3. It is less than or equal to 5. Isn't it?
Mm-hmm.
Yeah.
Directly, without considering the absolute value sign, you have minus 3 is definitely less than or equal to 5, correct?
Yes.
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 But you cannot say that minus 3 is less than or equal to minus 5, can you?
No.
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 Rather, you can say that minus 5 is less than or equal to minus 3.
Yeah.
Yes.
So whenever you see this, you write it in two ways. It actually means that minus c. Now, this means that you can combine them. Minus 5 less than or equal to minus 3 less than or equal to 5. If you combine these two together. Did you see this?
Yes. Yep.
Alex? I need Alex to respond all the time because sometimes I can't read your face to know if you get what I'm saying or not. So let me go back again. So this will happen if I need to negate what I have in the bracket, because this x in the bracket could be exactly this, or x could be a negation, right? So can we say minus x is less than that? No. Rather, it's going to be minus x is greater than that. So the second possible scenario will be that, okay, if absolute value of x, let me write here. If absolute value of x is less than or equal to 5. Remember, it is absolute value. So it could be a positive number in here, it could be a negative number in here. If it is a positive number in here, I can have, are you listening? Oh wait, let's look at it graphically. Let's look at it graphically. Let's consider the graph of absolute value of x. Graph of absolute value of x is like this. Do you agree? And if this is 5, then we're actually talking about this region. These are the region less than or equal to 5. Okay?
Yeah.
Now, graph of absolute value of x is this. If this is y is equal to 5, we're talking about this region. Now, what at this point? But at this point, you may have your, if I have my 5 is still within, my 4 is still within, 3 is still within, right? 0 is within it. Minus 1, minus 2, minus 3, up to minus 5 here. Okay, so how do we interpret this in terms of x? So if absolute value of x is actually less than or equal to 5, then either your x is less than or equal to 5, which covers this, or wait, yeah, say something.
Well, when x is not in absolute form, why not like include a negative as well?
Yeah, I'm just talking about this region.
Okay.
This region less than or equal to 5? Yes. Okay. But alternatively, the negative part, okay, this negative part. So x could be, what I'm saying is, x could be from minus 5 up to 5. Isn't it? So if I have a negation of x, so my negation of x, for example, maybe the negation of 2, opposite of 2. I'm not getting what I want to show you. Yeah, and I keep getting alarm as if I'm in school. What I'm trying to show you is this. This is actually the same as minus 5, because if you look at it, the region is from minus 5 to 5. You see, x lies within these two regions, isn't it? Hello, x lies within these two regions. So minus 5 is less than or equal to x less than or equal to 5. Do you agree?
Yes.
Because these are the points where, you know, you have below the line y is equal to 5. So it lies within here to here, just like your interval in domain. You say, oh, from -5 to 5, something like that. And what does this mean? It means -5 is less than or equal to x less than or equal to 5 for you to have this inequality. Again, how do I get this? From here, you draw the graph. Less than something, you have done modulus inequality, you have done normal inequality, right? And what we normally do is to consider the region below the line. Is that not? So you are wondering what part of this will be below the line. Am I making sense? Below the line, y is equal to 5. Below the line, y is equal to 5 is within here and here, including the point on the line. So it's actually from -5 to 5, which is this. So you will realize that if you have absolute value of x less than or equal to 5, you're actually considering x less than or equal to 5 and then -5 less than or equal to x. Did you see that? So which means this is your normal x less than or equal to 5. However, this is actually what? Minus x, is it? Less than 5. This one. Because if I move x to the other side, it's minus x less than 5. So why do we have those two possibilities? Because it's an absolute value function. So if you have this, I'm not sure if x is positive is the same, or maybe when the negation of x is less than it. Again, if I have absolute value of x less than or equal to 5, if my x is positive, it means x is less than or equal to 5. If my x is a negative number, it means that negative number is less than or equal to 5. That's why you have two possibilities. But you don't need to memorize all this. All you have to do whenever you have this kind of situation is to write in a combined inequality form. Did you notice what we have here? It's to write in this form. So this, just write negation of this number first, less than or equal to ax plus b, then less than or equal to c, just like we have here. Are you listening? Please stop writing and listen. Everybody get this?
Yeah.
Everybody get this point?
Yeah.
So that's the only thing you just need to write. Just interpret in this way. I hope no one is confused. No? Now, if you have inequality on both sides, this is when you square. You have absolute value, I'm sorry, on both sides. Less than or equal to cx plus d. Just square both sides. Square both sides. Okay, because it might be too complicated to write this. Square both sides, then you have your ax plus b. Of course, if absolute value shows you the order, it means that this is always less than this, and both of them are positive, right? When you square two positive numbers, they still maintain the order. So for example, if this is positive and this is positive, it's more or less 5 less than or equal to 7. By the time you square it, you still maintain that order.
Yeah.
Right? So which is why you can write, when you square both sides, you can say that, oh, this squared is still less than or equal to this squared. So this will give you a quadratic inequality, which we have solved in the class. You construct a quadratic inequality, you write your sign diagram, remember that, and from the sign diagram, you bring out your solution. Does this make sense?
Yes.
So let's go through one example quickly. Let's go through one example quickly. Again, okay, again, this is for the case of less than. If it is not the case of less than, you have to separate the two stuff. So let's listen to this first. I think I'm going to write one more. You can't hear anything, right?
There's no audio.
Can you hear anything?
No.
All right, let's try it again.
Modulus inequalities need to be solved with care because we need to consider several things at once. Firstly, we have seen that absolute value functions have several pieces or branches. Secondly, if we multiply or divide both sides of an inequality by a negative, we need to reverse the sign. We therefore want to study a modulus inequality carefully before we decide which method is most appropriate for solving it. In both of the inequalities in this example, we have the absolute value of a linear expression on one side and a positive constant on the other. We can solve these inequalities by separating the inequality into two pieces. To do this, think about the meaning of the absolute value function. In part A, the distance from 2x minus 1 to 0 is less than 3. So 2x minus 1 must lie between minus 3 and plus 3. We add 1 throughout, then divide throughout by 2, which we can do because 2 is positive. So x can take any value between minus 1 and 2.
Understand this?
Yes.
So just interpret this directly because it's in less than form. I haven't written this form. I skipped that. I don't know why, mistakenly. For this one, you don't write directly because remember that's a greater than. Let's look at it from the graph first before we listen to the example. That should actually have been the number 2. I hope nobody has written this. So let's look at the graph when it is greater than. So if it is greater than 5, we are talking about the region above. Do you agree?
Yeah.
We're talking about the region above. So if absolute value of x is greater than or equal to 5, so it means x is greater than or equal to 5. That is from here above, right? And also when x is less than or equal to 5. Can you see that? Minus 5, I mean. So which means either x is greater than 5 or minus x is greater than 5. You see, there are two things here. Either your x is less than or equal to 5. Hello? Either your x is less than or equal to 5 or negation of x, look at this one, or negation of x is less than or equal to 5. Same direction. But here, either your x is greater than 5 or your x is less than or equal to minus 5. If you apply the negation, yes, you can still maintain that direction. So by the time you have this the greater than, there will be two different, non-combining solutions like this. So if we're going to write this, just maintain, it's going to be the region after. So just remember this graph, picture this graph in your head. It's going to be the region above the line. So at the first extreme, it will be more than that number. At the second extreme, it will be less than negation of that number. So just try to remember this too. Do you understand?
Yep.
Okay, now, let me write that properly. Let's listen to the example. Then after that, I will give you a summary notes. Can you see the screen again?
Yeah.
Okay.
In part B, the distance from 4 minus x to 0 is greater than or equal to 5. So 4 minus x could be minus 5 or less, or else it could be 5 or more. We now solve the linear inequalities individually. For the first inequality, we add x and 5 to both sides and find x is greater than or equal to 9. For the second inequality, we add x and subtract 5 from both sides and find x is less than or equal to -1.
Can you see this? So these are the extreme points. You picture the graph. Absolute values graph is like this. Okay. This line is the line y is equal to 5. Okay. So when you're talking about greater than that, you're talking about the region above the line. For the region above the line is definitely from that point up to infinity. The other one is also from that point to negative infinity. So on the left-hand side, it's going to be less than or equal to -5. On the right-hand side, it's going to be more than 5. Does this make sense? But for this one, it's just a direct, because this is definitely it's within an interval. Below the line, it's a continuous interval, isn't it? You understand what I mean by continuous? It's a continuous interval from -3 up to 3 directly. But for this one, it's not continuous. It's coming from negative infinity up to -5. It's going to stop because now the line is broken into above and below. Then it's going to start again when it is above. So just picture the quadratic inequality that we did with the SL group. And I think that will help you a lot. So that's that. Go back to the screen. So let's write this properly. For absolute, let's write this together. So tell me what to write. If it is greater than or equal to C, it implies what? What is the first one? AX plus B.
AX plus B is bigger equals to C.
Bigger, sorry.
Start from the left. So which one is on the left? Picture the graph on the left. Yes, I'm waiting.
Smaller than -2.
Smaller than, look at the graph. Why is everyone quiet except Elsin? Look at the graph. Picture the graph like this. This is the graph of the absolute value. Now, this is the line y is equal to C. I think I should draw the graph too. Maybe that will help. Okay, I should draw the graph as well. So this is the graph. So
negative
when it is
C.
greater than, so you have, yes.
Wait.
You have your CC here. So I'm using absolute value of x less than or equal to C and absolute value of x greater than or equal to C, for example. So this is the one we are trying to interpret. Greater than or equal to C means from here and from here. This is the greater than part. This is the greater than part. Can you see that?
Yes.
I think I'll also color code this so that it's easier when I draw the picture. Sec, please. No. Back. Put the graph below. It's okay to put the graph below. Okay. If I put the graph in here, I hope I'm not confusing you. Guys?
Yeah.
I hope I'm not confusing you.
No, you're not. No, you're not.
Okay, thank you. So let's have one is no, not here. Find the line. Okay. Something like this. Now, this is the line y is equal to C. Okay. So this is the line y is equal to C. This is the graph f of x equals absolute value of x. So when we are talking about case 1, we are talking about this region. The first case is this region. Okay. First of all, think including that, right? So this is our C, this is our negative C. So for the first one, we're talking about the region in here. No. Yeah, when it is less than, on the graph, it's actually on the line. Region where the line is less than. So we're talking about from here to here. Do you agree? From here to here.
Yeah.
So, should I shade everything from the line? You know, it's just from this region to this region. It doesn't matter. So here, when the graph is less than
or equals to.
So it means the point where, you know, it is below. Okay, so maybe I don't need to shade. So it is below here, from here to here. Just trying to do some picture form. Sorry. So you're talking about from here to here. But when it is above, then you're talking about, right? This is the region above to infinity. Okay, so here is our case 2. This is case 2. But in here is case 1.
For case 1, when it's not equals to, when it's not greater than or equals, when it's not less than or equals to, and it's just less than, how do you write that 0 is not included?
Then it means you don't consider the exact point of intersection.
So how would we write that?
Same, just remove the equals to.
Yeah, you just don't have equals.
Just remove the equals to. Same.
Oh.
Okay, so let me write here. This is case 2. This is case 2. And in here is your case 1. Does this make sense? Makes it easier? All right. Let's write this properly. So for the case 2 now, it means this function is less than or equal to what?
Negative C.
Negative C, or the function is
greater or equal to
C.
So these are it. So the picture will really come in handy. If you don't mind, just have the picture at the back of your mind. It will really help. So same happens with, you know, when you have a rational function, you maintain the same thing. You maintain the same idea, and then you can cross multiply and whatnot. I'll show you what we need to do. So for the third one, if you now have this on both sides, ax plus b less than or equal to cx plus d absolute value, just square both sides, it's easier. Avoid dealing with 4 cases. Understand? Because you don't know if this is positive or negative. You don't want to do cx plus d less than or equal to ax plus b, minus, then less than or equal to cx plus d using case 1. Then if you want to use, now you don't know if this is positive or negative. So it's possible this is positive or negative. You don't want to create unnecessary confusion. So the best thing is to just square both sides. If both of them are positive, they maintain the greater than or equal to or less than or equal to. If both of them are negative, they still maintain the greater than or equal to or less than or equal to. So I think I should add that for greater than or equal to, for that, or absolute value of that, square both sides. So that when you square both sides, it's either you have ax plus, brackets and square. So it will imply ax plus b all squared less than or equal to cx plus d all squared, or you could have ax plus b all squared greater than or equal to cx plus d all squared. So is it that you have these two? And then you can solve, get your quadratic inequality, use your sign diagram, and do what we did in the SL group with the SL class. Okay. So, which gives, I'm just going to say which gives some quadratic px squared plus qx plus r less than or equal to 0, or px squared plus qx plus r greater than or equal to 0. So because it will lead to quadratic, clearly. Okay. So this is not something difficult, which is why I put it for these 2 days, because all you have to do is interpret, and that's it. Now let's take one example together. You have listened to one. So let's, okay, maybe I play you another example so we don't waste time. I think the audio is not, is self-explanatory, isn't it? Talk to me, guy. Is this self-explanatory?
Yes. Yeah.
Okay, great. So now check this out. You see, this is what we just talked about. For modulus inequality, where we know each side of the inequality is positive. How do we know it is positive? When we have absolute value, or when the number is a positive number, you can square both sides. So even for this is a positive number, this is a positive number. You can square both sides as well. Are you with me?
Yeah.
Because both sides are positive, so you can square both sides. You can square both sides. Now, let's see. I think those are the only 2 examples that was done. So let's not you, this one. Okay. Give me a thumbs up if you can hear the audio when I play it.
Modulus inequalities need to be solved with care because we need to consider several things at once. If we know that both sides of a modulus inequality are non-negative, we can square both sides. It is vital that we know both sides are non-negative, because if we multiply both sides of an inequality by a negative, we would need to reverse the inequality. In both of the inequalities in this example, we see that both sides are indeed non-negative. So, in part A, we begin by squaring both sides. The square of the size of an expression equals the square of the expression. We expand both perfect squares, then rearrange the inequality so all terms are on the left-hand side. We are left with a quadratic inequality. Can we factorize this quadratic? There are no common factors and no special form. 5x squared is the product of 5x and x. We search through the factor pairs of -8 to find 2 numbers which will give the correct middle term. We find that -2 and 4 give us the correct middle term. The zeros of the quadratic are -4 and 2/5, so we can use these to draw a sign diagram. The coefficient of x squared is positive, so the signs must read positive, negative, positive. So the quadratic is greater than or equal to 0 when x is less than or equal to -4, and when x is greater than or equal to 2/5. These are the solutions to the original inequality. In part B, the absolute value of the fraction is greater than or equal to 1/2. You might be tempted to try to solve this using the method of the previous example by separating the inequality into 2. If we did this, we could correctly say that the fraction must lie between -1/2 and 1/2 inclusive. However, we would at some point need to multiply throughout by x plus 1, and we cannot do this because we do not know whether x plus 1 is positive or negative. So we instead rely on knowing that both sides of the original inequality are non-negative, and we square both sides. The square of the size of an expression equals the square of the expression. We use the exponent law that a fraction to a power equals the numerator to the power over the denominator to the power. We can multiply both sides by 4 since 4 is positive. Since the perfect square of a real number is non-negative, we can multiply both sides by x plus 1 all squared. However, since we no longer see the factor x plus 1 in the denominator, we keep track of the fact that x equals minus 1 cannot be a solution. If we let x be minus 1 in the original inequality, the left-hand side would be undefined. We can now expand the perfect square, then rearrange the inequality so all terms are on the left-hand side. We are left with a quadratic inequality x equals minus 1.
Well, the audio is faster than what we can see.
Yeah.
However, since we no longer see the factor x plus 1 in the denominator, we keep track of the fact that x equals minus 1 cannot be a solution. If we let x be minus 1 in the original inequality, the left-hand side would be undefined. We can now expand the perfect square, then rearrange the inequality so all terms are on the left-hand side.
Someone is
We are
typing
left
instead of
with a
listening.
quadratic inequality. There are no common factors and no special form. 3x squared is the product of 3x and x. Minus 1 is 1 times minus 1, and we can arrange these factors to give the correct middle term. The zeros of the quadratic are minus 1/3 and 1, so we can use these to draw a sign diagram. The coefficient of x squared is positive, so the signs must read positive, negative, positive. So, the quadratic is greater than or equal to 0 when x is less than or equal to minus 1/3, remembering that we must specifically exclude minus 1, and when x is greater than or equal to 1. These are the solutions to the original inequality.
Who was that typing instead of listening?
It's me, Mr. Daniel. My mom's asking me to go eat.
Okay. All right. Now, so again, the reason, I hope you heard the audio. You could, if you want to use, let me go back to that. If you use this idea to split it, let's try to see what happens. Absolute value of x over x plus 1 is greater than or equal to 1/2. Of course, from what we have done, you can say x over x plus 1 will be less than or equal to minus half, the extreme, right?
Yeah.
Let's remember this picture. So this part and this part.
Mhm.
Or x over x plus 1 is greater than or equal to 1/2, which is this part. Then you have a problem. You can multiply by 2. 2 is positive and nothing will change. But you cannot multiply by x plus 1 because you know nothing about x plus 1. You don't know if it is positive or negative. If x plus 1 is positive, you're going to have to change the sign. If it is negative, you understand what I mean? Normally, we're supposed to multiply by 2 bracket x plus 1 to clear the fraction, yes?
Yeah.
But we don't know if 2 bracket x plus 1, if it is positive or negative. We don't know. So which means we don't know if we are to reverse the sign or not. So that is why when you have a situation like that, it is just better to square both sides. It's different from when you have x plus 1/2, absolute value greater than or equal to 1/3. It's different. In this case, you can you can do it. X plus 1 over 2 is less than or equal to minus 1 over 3, right? And x plus 1 over 2 is greater than or equal to 1 over 3. So here you can multiply by 6. Do you agree?
Yeah.
You can multiply by 6 to reduce the fraction. If you multiply by 6, you have 3, and you have 2. Please don't cross multiply. Do not cross multiply. Multiply by the LCM, not cross multiply. I hope I mentioned that during the linear inequality class in IGCSE days, I'm sure. You don't cross multiply. Because if you say A over B is less than or equal to C over D, if you go this way, you get AD first. If somebody goes this way, they get BC first. So how do you know which is correct? So it's better, just clear the fraction. So the reason why squaring both sides is essential here is because of x plus 1. You cannot multiply through by x plus 1. So let's be careful on that. Any questions, please?
No.
Okay. So because of our time, we won't waste too much time trying to practice. I'll leave you to do your practice on your own. Please, this part is very important. Even when you cross multiply, always include where x is not equal to minus 1. And of course, you don't have to try to use the scissors method. You know how we factorize normally. Write in 4 terms and factorize the way we do in the class. Am I making sense?
Yes.
Yeah.
And if one of the solution includes that number that is supposed to be excluded, you must write it that it must be excluded. Because if you look at it, this region, which we are supposed to consider, what is Mr. Iron Man doing? You're not focusing. I think you're doing something. You're covering your mouth, you're smiling at something, you're just making fun of something. What's going on? What's going on?
Yeah, I was looking at my phone.
Why are you looking at your phone?
I got a message from somebody. I'm sorry.
Gosh. If your x equals to minus 1 is included, because clearly minus 1 is in this region, it has to be clearly stated. That is why you must, from the point where you cross multiply, you must maintain that removal. You must remove it. You must remove x is equal to minus 1. Because when x is equal to 1, minus 1, it is undefined. Understand? When x is minus 1, it is undefined. So please be careful. You're going to see the same thing here. In this case, what must you remove?
Plus 2.
X is plus 2. You must say provided x is not equal to 2. Here, you must remove 1, and here you must remove half. However, if this point that have been removed are not within the solution, you don't have to include it. For example, instead of minus 1 over 3, if this was minus 3, remember, it's already left minus 1 behind. Do you understand? In that case, you don't have to bother x is not equal to minus 1, because even your region x less than minus 3 does not include x is equal to minus 1 anyway. So no need to add it. Am I making sense?
Yeah.
Yes.
Okay. If anybody adds that, it's going to be tautology and may penalize you for thinking like that. So for graphical approach, so we can, do you have your calculators?
Yep.
No.
So there's a calculator with you there, Yanko.
Yeah.
So just use what others are doing there. So can I ask you to try this? I will also save this and send to you. Can you still see the screen?
Yeah.
Yeah.
Okay. That will be sent to WeChat, so you can check it on WeChat.
Mr. Daniel, I got it.
What? So check your WeChat. For the full file. So go through the steps using the file on your WeChat. So please make sure you use that for question 4. I'm going to be sending you the screenshots of the pages and please practice. Tomorrow we have math class. I would like to see everybody look at the textbook because I'm going to close the class now. So you guys can, you said you have some stuff to do together, right?
Yeah.
So I can leave you be. I'd like to see, take note of this. At least take note of the last question in each. The last question in each, at least. If you can do the last 2, it's okay. Or let's make it look like I want to give you homework on modulus equation and inequality. So maybe I will type something and give you tomorrow. But for your own practice at least 1 from each of number 1 to 4. Understand? Practice at least 1 on your own. And if when I type it out, it happens to be what you have practiced, then lucky you. Okay? But what I'll be grading, practice at least 1. Okay? So I'll be sending you the screenshot of these pages just like we did yesterday. Any questions before I close the class?
No.
Right. If we are going to practice, it will take us more time, but I think you can do the practice on your own. So I don't need to keep you here. You can do your practice while you're having your fun there. I've not seen Elson's face. Can I at least see your face before we go? Okay, there he is. Okay. See you guys. Enjoy your time together. Bye. See you tomorrow.